When you're expressing properties of your programs in the Haskell type system, so if you're trying to do a bit of exciting type level programming, then you sometimes run into challenges with the Haskell class system. And we're going to look at one such scenario in today's episode where we're trying to express a constraint that ranges over a type level list.
Yeah, so welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, the show is live streamed, so we invite you to submit questions or comments in the chat, and we will try to show them on screen and discuss them.
Yeah, okay. So the starting point for today is a heterogeneous list. So a heterogeneous list is essentially like a list, but the elements in the list can be of different types, right? And that all in a type-safe way. Another way to think about heterogeneous lists, which I also sometimes like, is to say that, like in Haskell tuples, you have one tuple type for every arity, essentially, but you don't really have an inductive structure. And heterogeneous lists give you kind of this structure by essentially saying you pick a length and the types of all the components, but you get a list-like structure over it.
So like a tuple of as long as you want it to be.
As long as you want it to be, yeah. So you have constructors that correspond to the list constructors, and so you have h-nil for the empty heterogeneous list, and you have this cons dash for the cons. And so we track in the type system how many elements and which types our heterogeneous list has. So if we have an empty heterogeneous list, then we have 0 elements. And so this is an empty type level list. So this is one of the cases where sort of the syntax of Haskell's lists is sort of clashing with itself. And you have to use this tick here to denote that you really mean an empty type level list rather than the list type constructor, right? So so that is an disambiguation here. And then cons takes an element of any type and an h-list of some other types and forms an h-list of x-cons xs. And then we make the cons constructor right associative, and then we can start giving an example. So if we can, for example, start putting true into such a heterogeneous list, and then GHC infers that this is an h-list which has one element which is of bool type, right? Again, this is like a type level list, and it indicates that our list has one element and that one is of bool type. If I add another element here, say, for example, a character like a lowercase f, then I see that my type changes, and I get a list that has 2 elements, a Boolean and a character, right? And if I add this type signature, and then later make a change, right? So for example, say, let's add a number as well, then I'm actually getting a type error. That's a good thing, right? All this is sort of like tracked, like which positions have which types. So if I change this type here, then it's okay again. Okay, so far so good. Now, what if I want to show this example, like for example, use show on example 1. If I want to say something like show example 1. And if I try to evaluate this, I get a type error. And that is not surprising because I don't have a show instance for my h-list type. So, well, let's try to give a show instance for our h-list type. So the first thing you could try is to just say deriving show. That gives you an error message that says, oh, no, I can't do this because you have used a so-called GADT as this is, right? Because the constructors have different result types. And then GHC generally does not really like to use this deriving clause and says, oh, yeah, you can use a standalone deriving declaration instead. The point of the standalone deriving declaration is that if we do this, you usually have to give the precondition for the instance yourself, which you don't do if you just write deriving. So in a way, you're doing a little bit more work yourself, and that sometimes helps GHC along. So we want to define something like show of h-list access. And so the point is we cannot obviously just derive this without any precondition, because the elements of the H list, they occur, and we have to be able to show them, right? I mean, like if we put a function into an H list or an IO action, we cannot show the H list. So we have to have some constraint here for the access. And that's our problem. Now there is actually a relatively simple way around this. We can just give an inductive definition, like do an induction on the type level list, essentially, and say, well, if we have an empty H list, that is easy to show because it never contains anything, right? We don't need any preconditions here, and that deriving instance declaration is actually accepted. And we can also show an H list of the form xcons xs if we can show x, and if we already can show an H list for xs.
Yeah, so when Anders says inductive, if that doesn't make any, if you don't know what that means, you can also think recursive, right? This is like a recursive definition.
Yeah. And now with these two deriving instances, we can actually show this. I mean, it's not a beautiful show instance because it unnecessarily puts the parentheses there, but I mean, it's okay, right? So it works. So this is good if all we want to do is show, right? But we might want to define other functions, and to stick a little bit with the theme, let's try to say we want to have a show-like function on HList, but rather than showing in the Haskell way, we just want to like put the textual representations of all the elements and separate them with commas. So let's try to define commas, which goes from HList XS to string as a first approximation. Again, we will probably need some kind of constraint. So for HNIL, we simply return the empty list. And for a single element list, let's say, we are going to just show X. And for a list which is of the form X on XS, we're going to show X and then put a comma and then call commas on XS. Okay, so now we get type errors, and they're understandable because again we need to know that the elements of this list are showable. And actually we can use the same solution. We could define commas not as a pattern matching top level function, but we could put it into a type class and then define an instance for the empty list and define an instance for the non-empty list. But then we kind of accumulate type classes, right? Because every time we define a function on HList, we have to define a new type class, or we have to find some other trickery. So
it's also kind of a non-idiomatic way of writing Haskell, right? It's not normally how we write normal functions.
Yeah, I mean, it's an option, and I don't even want to say it's necessarily a bad option, but it's good to at least have other options on the table as well. And so the other option would be to somehow express what I just said in words, namely that what we really want is that the show constraint holds for all elements in this type level list XS. So if we had something that allowed us to say all show XS, with that meaning that show should hold for all the elements in this list XS, that would be great, right? So unfortunately, we can actually just write this. And so for this, we use a type family. So that usually does computation on types, but it's an interesting type family because it actually computes something that goes to the left of this double arrow. So it computes a constraint. And that is something that Haskell also allows us to do, and perhaps not everyone knows. So we can define type family all, which takes a C as an argument, which is supposed to be something like show, essentially a name of a class, and a type level list where all of C of, let's actually do this in a moment. Let's briefly talk about the kind of all. just to make this a little bit more precise. So as I said, C is supposed to be something like show, but if you think about show is something which itself takes an argument, which usually is a type, and then produces a constraint. So that's the kind of C, and then the access is a list of types. It's a type level list of types, and then in the end we get a constraint out.
Right. So if we have type to constraint, the type would be something like show int. The int would be the type.
Yeah. And so now we can do again induction on the type level list. So if we have an empty list here, then we want the empty constraint, and Haskell allows us to use certain syntax for constraints, right? So the empty constraint is written like the unit type is sort of an ad hoc disambiguation going on because we have this kind signature here. So this is actually needed here to put the kind signature, because if we didn't do this, JC would think that this is the unit type that we mean. But because we have this one, and if I have xcons xs, again we have sort of a pair syntax for concatenating constraints. So we can say we want the constraint C of x and the constraint all C of xs.
And of course, this pair syntax is common, right? If you have a normal function like foo of type, like eq int, or eq a show a, then we have a pair there as well.
Yeah. Right. I mean, we can put other constraints here with the same syntax. But
right.
Yes. Okay. And now commas type checks, and actually commas hopefully actually also works. So let's try commas on example 1. And indeed, it does have the expected result. And we could also replace our original deriving construct here, which is fine, but just to demonstrate it, we could also replace this with just saying if we have all show of xs, we also have show of h list of xs. This actually requires undecidable instances, but I think we've mentioned this before in some of our episodes. We are not really afraid of undecidable instances, so let's just add undecidable instances. Okay.
There's a quick question I think that's easy to answer at this point.
Yeah.
And it's a question from Pi. Is it possible to disambiguate in a different manner? Like if you did want to have to constrain?
Oh, yeah, I think so, but let me see. I mean, I think you can probably do something like
something
this.
Like this.
Yeah.
It's a bit messy. Yeah.
But if I omit this, then suddenly I'm getting errors elsewhere, right? So now I'm getting that constraint cannot be matched and with star. Okay. Okay, so this is good, right? And I mean, this gives us a useful solution to our original problem. So now I would like to generalize a bit. So let's look at a generalized form of the H-list type, which I'm calling product here. And this actually goes back or connects perhaps a little bit to the episode we did on higher kind of data types, where we talked about essentially record types or product types, where every component is additionally has a type constructor wrapped around them that you can choose yourself, and the step from H-list to product is exactly the same thing. We just abstract from an additional type constructor, and so here again we have two constructors which I'm calling slightly differently, just so that I don't have name clashes. So I say nil for the empty list case and colon star for the cons case. And now instead of having just an x, I have an f of x, and I carry this f around. So if I wanted to And I should also give the same infix declaration again. If I wanted to basically define the example again, example 2, I would now have to wrap all my components in some type constructor, for example, in the identity type, if I really just want effectively the same heterogeneous list in here.
Here, you mean colon star there, not colon dash.
Yes. Thank you. And I put nil, then I get correctly inferred that this is a product of identity of 3 components, bool, character, and integer. But now I could, in principle, I could choose other applications than identity, like the constant type constructor, or maybe, or IO, or list, or something like that. And we'll see another example like in a moment. But for the time being, let's just look at this identity scenario. The same problem as before. If I want to show this, so if I want to do show of example 2, then obviously right now I'm getting a type error because I don't have a show instance. And how can I do this in this case? So again, I can give this what I'm calling an inductive definition if I want. I can do that first. I could say deriving instance show of product f of the empty list and deriving instance show of product f of xcons xs. And what do I need for xcons xs? This time I need that f of x is showable, right? Because that is the thing that occurs here. And I need that product f xs is showable because that is the component that occurs here.
Recursive case, basically.
If I have these 2 things, then again, it just works. Now, can I also use all or some variant of all? Well, actually, I mean, one thing I could do is I could add this extra argument to all as well, just like I added an extra type constructor argument to product compared to HNIL, I could define a version of all that has yet one more argument for this type constructor. But I can also do it with all alone, but I'm running into a certain problem, because if I want to express, say, what I need to write here in order to give show of product xs once and for all, I cannot just write all show xs. I need to wrap all the xs in f, right? So either I need to I map on the type level f over xs first, or I need to write something here which is like, this is not something which is possible in Haskell, but what I would like to write is something like lambda x show of f of x on the type level, right? For every element in the type level list xs, which I temporarily call x, I want that show of f of x holds.
Maybe one day.
Maybe one day, yeah? Type level lambda is one of the things that, people have been working on this, and there have also been some proposals that go in that direction, but we don't have that. But an observation is that this is effectively type level composition, right? We like lambda x show of f of x is just show compose f on the type level. So if we had show dot f, yeah. So if we had some type level composition, let's say compose f g x is f of g of x, right? Then this could be written as compose show f x, and then we could eta reduce, right? Like get rid of the lambda and get rid of the x. It all sounds so nice, but unfortunately that still does not work, because type synonyms in Haskell have to be fully applied. And here the compose has 3 arguments, and we are giving it only 2, and that is exactly the type error message that we are getting here. And again, like if we wanted to give it 2 arguments only, we would have to put this as a lambda on the right hand side, and we cannot do that. So it's essentially the same constraint. But we don't need the general form of compose here. We need a form of compose that produces a class, a constraint. And I think we pointed this out in a couple of episodes already. You can, you can define something like class aliases in a nice way, using sort of like a certain programming pattern where you write a class compose FGS, and then you make the right-hand side of your original synonym a superclass constraint of this, and then you define an instance which has exactly the same shape. Now this again, this yields another sort of complaint by GHC that we have to enable undecidable superclasses, but for similar reasons why we're not afraid of undecidable instances, we're also not afraid of undecidable superclasses. So I'll just add this, and then this is accepted, and then I'm slightly surprised now that I'm not getting an error about overlapping instances, to be honest. But it's probably just because I'm not using this yet. Probably if I would refresh here. Yeah, then I'm getting an overlapping. It's because I have both the old definition and the new definition in. But I can remove this one, and then I can refresh again. And then I see that my new version works as well. So a little bit more on this here. Why is this working? So really, what we're doing is we're establishing actually a kind of equivalence between these two constraints, compose FGX and f of g of x. And despite sort of the direction of the arrows not really giving this, the class declaration actually gives you something which is more like compose FGX implies f of g of x, in the sense that if GHC knows compose FGX in a particular context, and something is a superclass of that, then it can go from compose FGX to f of g of x. That's basically what superclasses express. And actually, I think PureScript, which is inspired by Haskell and has a lot of Haskell syntax, but I think PureScript flips the arrow here. So I think that is actually perhaps a nice idea. And this one really gives you the other direction. And we can make that even more precise if you don't believe this by going back to something which is from the computing dictionaries, or inspired by the computing dictionaries episode that we also did. So if we have a dictionary type that is defined like this, we can actually write functions that turn one constraint into the other. We can do something like toCompose, which goes from a dictionary of f of g of x to a dictionary of compose FGX. And the idea is that if we have one, we can just turn it into the other, because they are synonymous, they are aliases for each other. And from
in this case, we're using the instance, right?
Yeah. I'll show that what happens if I remove one of them in a moment, right? But from compose is the other direction, and that also works. And yeah, so if I'm right, so toCompose is using the instance, as Etzke correctly remarked. So if I'm removing the instance, then toCompose should fail, and indeed it does, right? And if I'm removing the superclass constraint, then fromCompose should fail, right? So and indeed it does.
Very nice.
I'm getting the error here. Okay. All right. Back to this. Good. Okay. So one interesting thing that you can do with products is you can chain them. You can do something. You can define a product of products. Nest them. Yeah. I mean, you could do that with H lists as well, but with H lists it's uncontrolled, right? Like H list, every element can be different. And of course you can have an H list, which in its first component has another H list. But if you have a product of product, you know that it's like really a two-dimensional matrix, right? And so that's the advantage, right? So like as an example, we could do example 3 to keep it simple and save me some writing. I could just simply take example 2 and put that into another product twice. And if I add the type signature here, I get an inferred type of product identity. So the outer product contains product and the inner product contains identities. And then we have a list type level list of lists here. This is the outer list has 2 elements and the inner lists have 3 elements, as expected in a way.
Just to be clear, they don't need to be the same, right? We could have
no, they don't. We could put a different. Let's just put true nil here, right? And now it's of course not type correct, but if I just and I need to put identity, yeah. But now, I'm getting bool character integer here in the first list, and in the second position I only have a single bool. Yeah. So it doesn't have to be a really like a sort of like a proper rectangular matrix. But like can have different lengths. That's true. If I wanted to do that, I would have to do yet some more work. So can we still show this? And actually, we almost can. The only thing I have to do, I mean, like if I try this now, I'm getting an error, and that's actually not like a great error. Like when I first developed this example, when I thought about this episode, I was I was a little bit confused by this one, because it basically just tells you that you don't have a show instance for this product. But why? You should have, right? Because like we're saying, we can show a product if we can show the components effectively, and we can show the components. We have established that. We have already shown example 2, and this one is no harder. So why can we not show this one? And the only reason is that we've now made product kind polymorphic, but all I haven't had made kind polymorphic, and all actually can also be given sort of a more polymorphic kind. And if we do that, because I mean, we have type level lists of lists now, and so we have it's slightly fancier. So
so before we had elements like bool and car, which are all kind type, but now we have elements in the outer list which are themselves lists. And so by restricting ourselves to arguments of kind type, we rule those out.
Yeah, exactly.
Unnecessarily.
Okay. All right. So the final example I want to show is that, like, if we now want to write a variant of our commas function on example 3, or on something that is such a product of products, and say we want to turn something which is a product of something into something which is roughly like CSV format, right? So we have a product of identity of XSS, like a list of lists, and we want to turn that into a string. And the idea is we do for nil, we produce the empty string. For x const x's, we produce actually some version of commas, but generalized to products, right? Commas that we already had written for H lists, but generalized to products. So I'm going to call that commas prime, and I still have to write that. And then a new line, and then CSV of XS. And commas prime, just copying in, because it's really basically just the same that we had already written above for H lists, but now generalized to products. So the only thing is that this type changes, and we have these additional pattern matches on identity here. Otherwise, it's the same function. But now about the constraints, right? So commas needs this all show access constraint. And we are calling commas on all elements of the outer type level list, right? So that means that we actually, for all elements in XSS, need to know that all show holds. So what we really would like to write here is all show XSS. Unfortunately, this doesn't work for reasons that we have already discussed, right? Type family all should have 2 arguments, but has been given 1. Type families, just like type synonyms, have the problem that they have to be fully applied. But fortunately, again, just like with compose, all is a type family that produces a constraint. And we have seen a trick or a technique that allows us to do this, namely this one. And we can actually apply the same technique. And the same technique is applied here by essentially just, let's rename the type family here to all F, that we can, like in the end, use the same name for what we want. And then define a class, all CXS, that is an alias for the type family. So that like is equivalent to all FC access. And again, we define the instance as well. Okay. And actually, at this point, all my type errors go away. Like, I mean, the whole program type checks. And we should actually be able to call CSV on example 3 and evaluate it, and we get the right result. Okay.
Very nice.
So that's more or less the end. I'm not sure whether we have any questions.
We have another small question also by Pi again.
Okay.
Can GHE infer the more polymorphic kind signature of all?
I think it does, actually, yes. I think it, where do I have?
Although it's kind of tricky because
no,
you then need to put a constraint on the empty one, I guess.
Yes, but I think, yeah, I think if you basically did what I did in between, so yes.
Yeah,
right, and everything still checks, so that already hints at it, but I could also explicitly try to ask for the kind of all F, and you see that it infers the polymorphic kind.
Just to be clear, we have polykinds enabled, right, as part of...
Yeah, so I'm using a recent GHC, so that means we effectively are using GHC 2021, and that means that we have all sorts of extensions enabled by default, including polykinds. Yeah. Good remark. So the one thing that I could still mention is that, like, I mean,
we have one other question. We might just came in, we might as well.
Yeah. No, yeah, let's give priority to.
So Yaro asks, are there any disadvantages to using the partial class trick?
No, I think there are not. I mean, so the disadvantage is it only works for classes, right? I mean, so you cannot do it for arbitrary things, but otherwise I think it is basically always preferable. In my experience, it's also nicer with respect to error messages, actually. It's one of the rare cases where something like something that is like better is actually also leading to better error messages, because in general, like if you write even if you don't intend to like partially apply a constraint synonym, if you define it using type, it will almost always be expanded away in error messages. But if you define it using class, you have a good chance actually still seeing it in type error messages, and that is usually more meaningful. So yeah, I think I'm not aware of any drawbacks.
Yeah, me neither.
Yeah.
We have one more question from Jack. Can using arity 0 type families help with not fully applying types? So could you somehow do some trickery there?
Arity 0 type families.
So I think what he means is that in the definition of all, you change the kind, right?
Yes, but the problem is that, I mean, how do you make the arity here in such a case smaller without getting to type level lambdas again? Like,
Yeah,
I mean, sure.
I think that's the point. If you make this arity 0 or arity 1, then you cannot pattern match anymore.
Yeah, sure. I mean, if you have a situation where, say, you have a type family foo, which ranges over something, right? So like over something and something else, and then gives you something. So let's say the kind of this one would be type to type to type, something like this, like has 2 arguments. And if you instead can make it like to emphasize your type to type to type by basically removing this argument and really say for just one input, I'm mapping this to a type constructor, yeah, then this is better. That is clearly, if you can do it, I mean, it's more restricted in your definition but if you can do it, like if you always have a type constructor you can return, then that is better, because then you can get away with applying it to only one argument. But
then you cannot pattern match on that argument anymore. Right? That's the point.
It's a real trade-off, and I think it's not a general, unfortunately, not a general solution. But sometimes it can help. Yeah. Okay. I think we are at a time where we can leave it at this. If there are additional questions, you can of course always still ask them in the chat or put them in the comments of the video later. Oops, sorry.
All right. So yeah, thanks everyone for watching. And if you enjoyed it, please like and subscribe. Feel free to leave any comments below the video, and we always try to keep an eye on those and answer them. And like Anders said, we keep the chat open for a few more minutes. So if you want to ask any more questions there, that's also possible. Thanks very much, and see you in 2 weeks.
Probably in 2 weeks, yeah. Thank you. Bye. Oof.